The title of today's webinar is The Lighting Passport Instrument Measurements and Their Interpretation. So this webinar is being recorded and the recording will be sent to you within a few days. So the reason for this title is that the reason for
I'll call you back.
Yeah, the reason for, can you please put yourself on mute, everyone?
Yeah.
Thank you. Yeah. The reason for the webinar, the title of the webinar is that on January 12th, I did a webinar, another webinar where I measured the spectra and all the other parameters of 4 different light sources using the lighting passport in real time. So I saved all those measurements on the cloud, the Spectrum Genius cloud, and I got a feedback from a few of our attendees that it would be nice if you do another webinar to interpret the result of those measurements. So, and this is what this webinar is all about. I'm going to just go through the results of those saved measurements on the cloud and explain everything, what we understand, what does these results mean. So the outline of the talk, again, interpreting the measurements of 4 different types of lamps saved on the cloud. And these lamps were LED 3000 Kelvin, LED 5000 Kelvin, an incandescent, and the office fluorescent. So we'll go through all the different parameters that were measured and try to interpret them. And then I would go through how to generate the TM30-20 report using lighting passport data and the online calculator. Then we would uh, again review all cloud features, including report generation. And then if there's any time, I'll talk about Annex E of the TM30. And last time there was also a little misunderstanding over the Spectrum Genius transmission average and photopic transmission. So I'll go through them as well. So here are the 4 lamps that we measured in real time in the last webinar. So you can see from left to right, you have the white, warm white incandescent lamp. It's a 100-watt lamp, and it's a warm light. Then you have the soft white LED. It's 90 watts, and it's about 3000 Kelvin. Then you have the daylight LED, 5000 Kelvin. And then finally you have the fluorescent light. So this, I had to climb over a desk to take a picture of this lamp because it's in a fixture on the ceiling. So this is also warm light. It's not a cool fluorescent, it's a warm fluorescent. So let me actually show the cloud first before I go through these. So if you go there, you see this is the Spectrum Genius cloud, and anybody could register for it. You can see my picture here. So if you go there to spectrumgenius.com, you can register your name, unique email, provide some basic information, and then you can make measurements with Sdcm Plus. And if you synchronize the cloud with the instrument, all your measurements will be saved on the cloud. And I can show you that. If I go back here, you can see these are the 4 measurements which I did on January 12th. Okay, so fluorescent, you can see the fixture here. Then you have incandescent, and then LED 5000, LED 3000. So if I click on one of these, for example, you can just wait till you can see the fixture here. Okay, and then you go to measurements, and then you would click on this link. So let's just give it a few seconds for it to load, and then it should show you all the measurements that were taken. Yes, there you go. So all the measurements. So you can see color, temperature, DUV, CRI, everything, Flickr, everything. So I'm going to explain all of these. What are all of these mean? And then you also have human photopigment, the spectrum, R1 to R15, TM30, CIE 1931, IEC SDCM, and this is also an ANSI plot of the SDCM. So some of you may wonder, what are these parameters? Some may not know all these parameters. So my goal in this webinar is to explain all the parameters to you. So first we start with the spectrum. So these are the four spectra that we measured. From top left, we have the incandescent. So the color temperature was measured at 2635, which is consistent with what is written on the box. So the incandescent light is a black body source. So it is a continuous wave, a continuous profile, I mean. So you can see it's rising here. And if you're wondering if this is rising forever, the answer is no, because the peak of a black body you can calculate by dividing 3000 by the color temperature, and you'll find what is the peak. So 3000 micron Kelvin divided by 2635 is roughly about 1 micron. So if this spectrometer could measure up to 1 micron, this would go all the way and then it will peak and then it will come down. But we are not measuring that. So this is correctly measured. Then you have the fluorescent light. So you can see all the typical peaks of the fluorescent light, but you can also see there is like a little baseline here. And the reason for this is because while I was measuring the light, there was some sunlight coming into my office as well. So it's measured a little bit of the sunlight as well. So that baseline is from the sunlight. Now here you have the LED cool at 4,624. It was a spec for 5,000. An LED warm CCT 3002. It was a spec for 3,000. And one thing that we should notice about this right away is that for cool LED, the maximum peak is at blue. And for warm LED, the maximum peak is at like near red, near 620. And this is the main difference between the cool LED and the warm LED, because the cool LED would have more of a blue light than red, green, yellow. And the warm LED has more of a green, blue, yellow, green, yellow, green, red than blue. So only by looking at the spectra, first of all, you can tell that this is LED spectra. And also by looking at which peak is higher, you can say if it is a cool LED or a warm LED. So that's an interesting observation that you can right away find. Okay, next. Next, we have the R1 to R15. So these are basically CRI indices. Okay, so the idea is that the CRI index, as I've explained in my previous webinar, they show how closely this basically light source brings out the true color of the objects. If you put an apple in front of a sunlight, you see the nice red color of it. But if you put the same apple in front of a mercury light, it may look a different color. So if the light source brings out the true colors, it has high CRI indices, up to on a scale of 100. So these are for different colors. You can see 90 for the incandescent light, which is a black body. It's like a sunlight. It has very high values, very high. So RA is the average of R1 to R8, which is 98, and RE is the average of R1 to R15, which is also 98. Okay, now then we go to fluorescent. Fluorescent, you can see the numbers are lower, and interestingly, the red R9 is negative. So some people are amazed by that. Why this is negative, and is this a mistake? Is there an error by the instrument? The answer is no, there's no error by the instrument. It happens that for some lights, for example, if you look at outdoor lighting, sometimes if you measure it, you see the R9 is negative. It's because the calculation of the CRI is in such a way that it would allow the indices to go negative, and it may happen that this becomes negative. It's very sensitive to the red, and it could go negative. So again, the average 83, R1 to R8, R1 to R1575. For the LEDs, you see the red is there. It's a small 12 and 20, but still positive values are A85, RE79, RA83, RE77. So I've plotted the same report for the fluorescent with the TM30, and you can see that for TM30 they have 99 colors instead of 15 colors. So although the values of red are smaller, they're not negative. They're about 60, 70. So the calculation method of TM30 has already taken care of this issue, that it would not allow the 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 CRI value to go negative. So you can see that the values are of the red CRI are smaller, but they're not negative. They're about 60, 70, whereas if you go to green, it could be about 90. And here is a link for the generation of this report that I will talk to you about later. We can use the lighting passport to generate this report. So I'll show you that later. This is also the full TM30 color rendition report. We are trying to include all of these graphs in the lighting passport data, but for now we only have this one, and even the format is not correct. So instead of the pie chart, we have like a checkered board. So we already know about this problem, and we are trying to fix it as soon as possible. All right, so next we go to color vector graphics. So if you go to the cloud, you can go to Spectrum TM30, you'll see it here. So these are the ones that we are looking at for the 4 lamps. So let's look at it and see what we understand from this. And do we expect these graphs or not? Okay, so in this graph, we know that incandescent light, when it is compared with a reference black body, is very similar, because incandescent is also a type of black body. So we expect the test source and the reference source to be almost similar. They coincide. So this is what we expect, and we have the fidelity index of 99 and the gamut index of 99. They're both very high. So that is all expected. Uh, Sent video was wrong, so I had to send. Yeah. So I just heard that the webinar link was sent again. I don't know if other people will start joining, but I'll continue anyway. So I don't want to get distracted from giving the talk. Other people could join, or we could repeat this webinar another time. Then we go to the fluorescent, and you can see there are these arrows here. What are these arrows indicate? So if there are inward arrows, it means desaturation. So this is desaturation. If there are outward arrows, there are saturation, and there are also some. So these show basically chroma shift, and if there are tangent arrows, it means basically hue shifts, the change of color. So anti-clockwise arrows represent, basically they represent positive hue shifts, and counter and clockwise show negative hue shifts. So you can see all these things at different regions. So for example, for red, you can see here there's in the red region there is a little bit of desaturation, and also you can say negative there's a negative hue shift. Sorry, go back again. So you can do your gamut index and RF fidelity index, and these are the values you get. Similarly, for the LEDs, again, we see some desaturation in the red, and the RF is an average of all the different indices there. So and RG also is kind of an average. There's some calculations that I talked about in the previous webinar, so I don't have time to go through this webinar right now. So this is the color vector graphics that will tell you a lot. In fact, in the TM30, they have other information that are written at the four corners that are important, but we still don't have that in the lighting passport. So hopefully we'll get it on the lighting passport soon too. All right. Next, we are talking about the CIE 1931. So what does this show? Basically, this is the chromaticity diagram. So each light source has a certain coordinate on this diagram. So if you look at it here, for example, you see this is the point for the incandescent light, and its coordinates are 0.46 and say zero point 0.4. And this black line, the curved black line, shows the black body curve. So these vertical lines, also the perpendicular lines, are showing the CCT lines. They have the same temperature. So if this point falls on any of these, then you would read out the temperature. Whether it's here or on the line, you always has the color correlated color temperature of 4000 as shown in here. So in this case, you can see, as we expect, the incandescent light is a black body, so it is falling on it, and its correlated color temperature 2635. For the fluorescent, it's a little bit above it. So this is related to the parameter DUV that shows if if the point is above the black body, is negative DUV, it's more greenish yellowish. If it is below it, it's more reddish, it's positive DUV. And similarly, the LED warm and LED cool, they're also at these temperatures, 4600. You can see LED cool is farther away, is here, is not at the peak of the black body curve, and it's over here. And for this one is still close. So they're almost on the line. So these are the 1931 that you can also see on the cloud. All right. Next, we go to TLCI. So again, I'm going to refer to the cloud one more time to show you that you can see all these parameters that I'm explaining right now are already given here. So I've extracted the information and I'm comparing the four lamps to each other. So let me go back and explain what TLCI is. All right. So TLCI basically is a standard presented by European Broadcasting Union, and it's a new evaluation standard for studio lights and luminaires. Basically, it mimics a complete TV camera and display, and it only considers the parameters that are related to color performance. It uses a color checker, the chart that compares the color rendering qualities of the luminaire to a benchmark, and it assigns a value from 0 to 100. So if the value is high, close to 100, it means that that particular light is very well with the television camera. So 85 to 100 is excellent quality with error so small that even a lighting engineer could not find it. 75 to 80, it needs a little adjustment. 50 to 75 may need a filter and more adjustment, and so on. If you are in this region, then it's hopeless. It's really bad lighting for the camera. So it considers the spectral performance of different wavelengths uh, based on what is seen by the camera, not by the eye. So that's the TLCI. And if you compare the measurements, you'll see LED 5076-73, incandescent 100, and a fluorescent 65. So the camera is really happy with the incandescent light, the natural light, and okay with the LEDs, and not so okay with the fluorescent. Next, we have the GAI definition, and this is kind of similar to calculation of RG. So RG in TM30 that I've explained in the previous webinars is a measure of whether the light is saturated or desaturated. But instead of the 99 colors that the TM30 uses, this only uses the 8 basic colors that are in the CIE. So you would just calculate the CRI index for each one, uh, for the test source and also for the reference source. And then you get these uh, basically polygons. So the ratio of the measured area basically of the test source by the measured area of the reference by 100 will give you the GAI parameter. So if it is a low GAI, it means that it's desaturated. If it is a high GAI 95, it shows good color discrimination, saturation, and vividness. So these are the measurements for the GAI: 78, 50, 44, 51. And if you have also written the RG, which is the equivalent in TM30, 96, 95, 99, 95. And one of our customer asked us a very good question. I said, I don't understand. Why is that incandescent light shows such a high value of RG, but in this GAI standard, it shows such a low or intermediate below average 44. So is this a mistake by the instrument? But so I dig it out. I consulted some people and I found out that this is not a mistake because for TM30, when it's comparing the reference, the test source with the light source, it uses a floating uh, reference source. So depending on the temperature of the test source, it uses a different parameter. So let me go to um, one of the other presentations that I have here, and I can tell you what I mean by that. So if we go to the TM30 calculations, yeah, right here you can see if the temperature of the measured temperature is less than 4000 K, they use a black body. If it is between 4000 to 5000, it uses a mixture of black body and CIE daylight. And if it is greater than 5000, it uses CIE daylight itself. So it's different. The reference chosen is different depending on the color temperature of the test source. But in case of the other one, in case of GAI, they always use one color, one source of a higher color temperature. So that will give wrong results or inaccurate results when it's applied to lower black body color temperatures. 2635 is quite low. So that's why when you do not have a floating reference, you keep your reference constant, this value that is produced for lower blackbody gives a low value, which is inaccurate. So for this reason, I don't recommend using GAI at all, and I would just focus on the TM30 RG and RF values, which are very accurate. Okay. Next, we also have CQS. This is also another color quality scale. You can see the colors are different a little bit. Like Q9 is greenish, whereas in the other case for CIE it was is red, and it uses basically a method for calculating CQS as derived from modification to the method used in CIE, and these are the values that you can see. You can compare this with the RF value, the fidelity index, and they're almost similar to the fidelity index by the TM30. So far, so good. All right. Now, another parameter, peak wavelength. Let's again go back to the spectrum genius, to the cloud, and see what I'm talking about here. Lambda P, 603 nanometer. So let's try to understand what this is. So all right. So each spectra has a wavelength that has its highest intensity. So that is the peak wavelength. And we want to know what is the peak wavelength for each spectra. So you can see we got 450 for 5000, 603 for 3000, 780 for incandescent, and fluorescent 610. And this is quite consistent with the spectra that we measured. If you go back to the spectra, you can see for incandescent, it's constantly rising. So the maximum is at 780. For fluorescent, it was around 620. For the cool LED, the blue is the highest, so it's 400, maybe 30. And for this one, the red is the highest, so it's about 620. So that makes sense. You understand that. Next is the dominant wavelength. What is a dominant wavelength is? So this uses the chromaticity. So remember we talked about chromaticity diagram, and here is the chromaticity diagram. So you have these yellow, this represents the light source. So if you join this point to the center of this cone, you can say, so the center is at the white point. If you join it to the center and then extend this line till it intersects the boundary. So basically the boundary is where you have only single wavelengths. So here is about maybe 600. So then that wavelength would be your dominant wavelength. So this is how it is done. So in this case, the point was here. So we joined that to the center of the cone, and then we extended it till it hits the basically the boundary, and that will be the dominant wavelength. So this basically represents, if you're looking at a wave, at a light that has many different colors, what color is more tending to? So is it more bluish? Is it more greenish? And you can also see that this would, if you extend it on this way, it's also intersecting, but you always go to the shorter distance. So where you have to extend it in a smaller way to hit the boundary. So that is the dominant wavelength. So 573, 582, 584, 580. They're almost the same. All of them are almost the same. And then you have purity. Purity definition. What does purity mean in here? So, so again, you extend it, you join it to the center, extend it till it hits the boundary, and then you take the ratio of the distance between the test and the center, which is here, to the center to the boundary, and that comes as a number that is as a percent that is less than 100%. Excitation purity is distance from illuminant point. This is illuminant point to the reference point. So this distance divided by reference point, which is here, to the spectrum locus, which is over here. So, so this distance divided by this distance, that will give you the purity. And if you look at it, you see most of them are 60%, and LED 5000 is 20%. So you may be wondering why. Why is that lower? And that is explained very well if you go to the curve, to the chromaticity diagram. You can see that the distance of the 5000 to the center is very small. So this compared to this is about 20%, but this compared to this is about 60%. And these three are almost similar to each other. So it all depends on where uh, the point falls on the chromaticity diagram. Usually when it's higher temperature, higher correlated CCT, it has less purity. Okay, next is the SP ratio definition. Again, you'll see, let me go back again, I'll show you. SP ratio. So SP ratio is given here 1.3. So I have put all of them in the 4 SP ratio. All right. So SP ratio is the scotopic vision divided by the photopic vision. So what is scotopic? Is the ability of human light to see in the low lighting conditions, dark conditions. And the photopic is the basically ability to see in the light in the lit conditions. And the spectral response curve of the eye varies. So you can see this is the photopic. Its center is about 555, and then you have the scotopic, which is at a shorter wavelength. So this is 507 and this is 555. So lamps with high S to P ratios also improve one's ability to see both low light and well lit conditions. So if a lamp has higher S to P ratio, if you turn down the power, you can see it better than another lamp that has a lower S to P ratio. When we look at our measurements, we see our LED 5000 1.9, and these other ones are 1.3. So if you turn down the power to all of these lamps, you can see the LED 5000 much better than the other one in low lit conditions. So the calculation of these parameters also takes into account the eye response function for the scotopic, shown in green, and the photopic, shown in gray. And this is the formula that calculates that. Okay, that makes sense as well. Now, circadian stimulus definition, these are all to do the parameters that are to do with the human-centric lighting. So one factor that is very much of concern is the suppression of melatonin by blue light, and that is not very good. That's why scientists don't recommend people to look at their cell phone before sleep because of the blue light coming from their cell phones, and that would suppress the melatonin, and then they can't fall asleep. So this parameter, circadian stimulus Cs, is a new metric that has been defined by the Lighting Research Center, and it has a range from zero point 0.1 to zero point 0.7. So a zero point 0.1 means it would suppress melatonin by about 10% after 1 hour of exposure. Okay, so obviously zero point 0.7 means 70% after 1 hour of exposure. So the lower this parameter circadian stimulus is, the better is for the lamp. So it would not stop you from sleeping. And when we measured it from the four lamps, we saw LED 5000, which is cool LED, cool light, is more white, has the highest zero point 0.7. And this is what we expect, because at night you want to have warm light, not cool light, because cool light makes you want to get up and do some more work, but the warm lights make you relax more. So that's why this has a zero point 0.7 circadian stimulus, and these guys have zero point 0.4, and this is also a warm fluorescent, so this is also very low. This is the reference for this calculation if someone is interested to know how this is calculated. We also have the circadian light definition. Again, this has to do uh, with the human-centric lighting, and this has been devised by the Lighting Research Center. So basically, this has to do with different photopigments uh, that exist in the eye, and circadian light is also, it's like a spectrally weighted function that is related to basically eye response. So you can see the measurements, circadian light, these are the values that are obtained, and these are the corresponding lux values that we got: 13,000, 546, 613, and 128. So two questions come to mind here when we look at these. First of all, someone may ask, why is that the LED 5000 is so high lux and LED 3000 so low? And the simple answer to that is, when I was measuring it, I kept because it was a measurement in real time, so I kept the LED light 5000 very close to the detector, and I did not keep the LED 3000 close to the detector. I didn't use the same distance. So I actually remeasured the LED 3000 by bringing it very close to the detector, and I got about 15,000 lux. So there's nothing, about the light. This is only the way I made the measurements. So this is one question. And this circadian light, you can read more about it in this reference, and I'm not going much into detail into that, is also spectrally a weighted function related to the spectral sensitivity of the eye and also the amount of light that there is. And it has a unitless value. So it's not in lux, but this is like a normalized value that is calculated. And these are the values that is obtained. If someone wants to know more about this one, you could go back and read this paper, Light as a Circadian Stimulus for Architectural Lighting, explain how this is calculated, the circadian light. So this is good for human-centric lighting. Okay. Next, let's talk about Flickr. So Flickr, there are three parameters of Flickr: the Flickr percentage, Flickr index, and Flickr frequency. So the fluttering of the light basically is Flickr, defines Flickr, and if it is at low frequency, it could have a harmful effect on the health of a person. And the first Flickr percentage, you could see there's a maximum and there's a minimum. So just calculate the Flickr percentage. A minus B divided by A plus B multiplied by 100% is the Flickr percentage. And the lower it is, the better is for not having the Flickr. And for example, in Japan, the percentage is less than 5%. So that is good. So what did we get? We got fluorescent 2%, incandescent 5%, and this is questionable because I remember when I did the measurement, I got an error, LED 3000, LED 5000. So we get to these two numbers later when we look at the frequency. So 2%, 5%, they make sense. These do not make sense. Then you also have Flickr index. So this looks at the area. So you take the average of the spectrum, which is this line, and then this area 1 divided by area 1 plus area 2, that will give you the Flickr index. So the less it is, the scale is 0 to 1. 0 means a steady light. Higher values means more increased probability of noticeable lamp flicker. So for this one, we got 0. 0.01, 0. 0.01, 0.05, 0.05, 0.01. Up to now, we can't really say much about this till we look at the frequency. And this is a discussion that we had last time, and our sales rep, Les, in California, made a valuable comment, which I'm going to explain in the next slide. So flicker frequency is how much fluttering there is, how many times it turns on and off, and that is an important thing to measure. Uh, Lighting Passport is capable to measure from 0 to 200 hertz. That's the capability of Lighting Passport. So what we measured last time was 120 for fluorescent, 120 for incandescent, and 1 and 2. So these two are definitely wrong because, as Les also pointed out last time, if it is a 1 hertz flicker, you should be able to see it. You should be able to observe that it is flickering with your eye. And we didn't see that, and 2 is like that as well. So these measurements were wrong, and we also got an error message when we did these measurements. So for this reason, I redid these measurements yesterday. So for the 3000 LED, I repeated and you can see I got 17,000 lux, flicker percentage 8%, flicker index 0.02, and flicker frequency 119, roughly 120. And the 120 flicker is understandable because you have a 60 hertz frequency for your electrical line, and a double of that would be 120. So that's the amount of time you see that the light is fluctuating. And for the 5000 also, I got 1% flicker percentage, flicker index 0, and Flickr Frequency 120. So these are correct, and these two are wrong from last time measurements, from January 12 measurement. These are wrong. So the way to measure it correctly would be if you have to put your instrument stationary with respect to the light source. They shouldn't be moving with respect to each other. If they are moving, you may get an error message, and the lighting passport will tell you. So go ahead and use your lighting passport and make a measurement by making it stationary. So most likely you'll get 120, or you could get a different readings. All right, and then the human photopigment definition. Again, there's this reference that describes that. So there are different, you can say there are different photopigments in the eye. There is the rhodopic, and based on each photopigment, there is uh, there is a particular lux. So you have rhodopic lux, which is detected by rods, which is basically low light conditions. Then you have three types of cone. The cyanopic lux, these are detected by S cone, that is short wavelength and color, uh, basically short color, blue color. Then you have the illuminance chlorophic lux detected by M cones, medium wavelength, and iritropic lux illuminance detected by L cone, which is long wavelength, so it's a red color. And you also have the EML, equivalent melanopic lux. This is detected by intrinsically photosensitive retinal ganglion cells. So that EML is quite important. And what are these ganglion cells? They're the final output neurons of the vertebrate retina, and they collect information about the visual world from bipolar cells. And this information is in the form of chemical messages sensed by receptors on the ganglion cell membrane. So they will transfer the information to the brain. So we have these photocentric uh, measurement, human-centric measurements for each type of lux, and these are the values. So of course, when you have a very high lux value, each individual lux from each photopigment also increases. So here we had a large lux for the LED cool. So melanopic lux 10,806, and all the other ones are high compared to the other ones. So this has to do with the physiology of the eye. If someone is more interested to know about these different photopigments, I refer you to this document. You can go and read this document to understand more. And now we go to Sdcm. What is Sdcm? Let me show you again here, Sdcm, what we are talking about. This is the Sdcm plots. Okay, so we already talked about most of the parameters: human photopigment, spectrum, R1 to R15, TM30, 1931, 1976 is similar to this. I'm not going into it. Now we are getting to Sdcm. So that stands for standard deviation of color matching. And what does it represent? So basically, this is measured by this Sdcm scale, and if there are these ellipses that are defined, they are called McAdams ellipses, and depending on where the light source falls, so the first one could be 1 Sdcm, 2 Sdcm, 3 Sdcm, 4 Sdcm. Depending on where it falls, you would be able to distinguish between different colors in the light source or no. So if it is 1 Sdcm, you cannot distinguish any color differences. If you look at the light source, you can't distinguish color differences. If it is 2 to 4 units, then the differences are barely visible. If it is 5 or more, then the differences are noticeable. So the lower the number of Sdcm, the better it is. You can't see color discrepancy, the color difference. So when we look at our measurements, you'll see that for the incandescent, it falls within the 5 Sdcm. So there are no differences are barely noticeable. So this is, if you look at the incandescent light, you won't see color differences. For the fluorescent, it's lying outside of 7 SDCM, so you should be able to see color differences. For LED warm, it's within the 5 SDCM, so you won't see color differences. And for cool LED, it's on the 7 SDCM, so you should be able to see some color differences. The same plot is the ANSI quadrangle definition, C78.377 2017, which you can see here in the right here. This is the plot there. And one thing I should also mention here is that for each light, you need to, if you're looking at the Sdcm plots, you need to adjust the color temperature. So if you look at this, what spectrum is it? First of all, this I can see from the spectrum. This is the warm LED. What is the color temperature? It's 3002 Kelvin. So when I go to the Sdcm plot, there this drop-down menu would allow me to choose the 3000. I should choose the temperature that is closer to the color temperature of the source. So 3000 would bring it here. You can see within 5 SDCM. But if I go 2700, it jumps out. So that's what you have to do. Similarly, for the ANSI plot, for this one, I have to choose 3000, and this would bring it within this quadrangle. This quadrangle loosely defines the 7 SDCM scale. So these two are kind of equivalent to each other, but this one has more details than this one. So anything within the boundary of this is like 7 SDCM, uh, McAdams ellipse. And when we look at it, we can see incandescent is well within, and these two are kind of on the boundary, and the warm LED is also well within, which is coincident to this one, to the SDCM measurement, the other measurement. So that would bring us, we have about 5 minutes. That would bring us to this. So I have put all the parameters here for each one, and I have described all of them except for DUV. I talked about DUV a little bit, that if it is above the black body is negative DUV, if it is below the black body is positive DUV. And you can see these are all positive. And then the PPFD, for people who are in horticultural light, PPFD values in micromoles per meter square per second is quite important, because plants like to have more, they care more about the photons of different wavelengths that falls on them rather than the total intensity. So you can divide the watts into how many photons are there, and micromole is just the scale, is 6.02 into 10 to the 17 is 1 micromole. So instead of saying 6.02 into 10 to the 17 photons, you could say 1 micromole. So in this case, you can see here for the LED cool, where we had a big lux, we have 194 micromoles. So that is also important there. Everything else I think I've explained here. There was one parameter that we didn't measure in our measurement last time. I didn't select it to measure, and that is the SSI parameter, the spectral similarity index. And that is also, again, for television camera, because the film industry uses film stocks that are designed for tungsten lamp and black body sources, but that's not the case now. The era is for LED sources. So the SSI parameter basically compares the differences of the light source that is used. You can see this is the LED source. It has two peaks, and this is the black body source, and it has highlighted the differences between the two. Okay, so it will measure these differences, and then it would do some calculation based on the variance on the difference. So you can say something like that: test minus reference. So it will subtract, these are all these subtractions, divided by the reference, the area of the reference, and that ratio If the two are close to each other, that ratio is small. If the two are far away from each other, that ratio is large. Then 1 minus that ratio multiplied by 100, that would give you a scale from 1 to 100, basically. So the higher it is, then the more suitable the light source is for the film industry, because that means that this difference is very small. And the lower it is means this difference is large and the light is not suitable for the film industry. Here is also my measurement of the fluorescent light, the SSI parameter of the fluorescent light, which turns out to be around 36.7. So one last point before we go to the questions. One very quick thing that I want to do is go back to the cloud. Just show you one thing very quick, how you can generate the TM30 report. We started 5 minutes late, so I hope you give me 5 more minutes on this. So if I go back here, let me first of all give you the spectral calculator link on the go-to meeting. So I will send you this spectral calculator. Control V, send. And now I'm just gonna do a calculation here. So this is the spectral calculator by the Illuminating Engineering Society, the IES, and how to use the lighting passport report to generate this report. So let's say we would select one of these. So we would select this, and then we would export the report. We can use export the report, and that would give us a file. Actually, export report. Yes. No, sorry. Download. We use the download, not export report. We use the download, and then it gives us a CSV file. So we just look at the CSV file, and this was for one of the LEDs. And then you would basically go ahead and copy all the absorbances here. Control C. Then you go to the spectral calculator. You would create a table, and then you put it on the first row of this and do a Control V. So you paste all the irradiances there and then say calculate. So once you see the calculate, it generates the TM30 report with all the RF, color fidelities, the hue shift, the color, the chroma shift, all the values, the color vector graphics. And then at this point, you can go the full report and download is there, the current report image, and then you could do a PDF, say high resolution PDF. You can generate a high resolution PDF out of it. And there you go. Here is the PDF. And if you look at it, here's your nice report that you can generate with the TM30 report. With the lighting passport data, you can generate the TM30-20 report. Unfortunately, I don't have time to explain the Annex E. Time is running out. So I I would stop at this point. I see that some other people have joined the webinar. I apologize for the confusion about the link. So there was some problems with sending the link, and at this point I stop. And if anyone has any question, please send me. I see there are some questions here. How far was the measuring device from the light sources? Okay, this question by Ruslan. So the fluorescent light, Ruslan, is on the ceiling of my office. So that would give us like maybe 500 lux, something like that. For the other ones, I try to keep it at a distance of about 30 centimeters from the detector. So I can show you show you what I used basically. So if you see my here is like the lamp that I had, the lamp fixture. So basically I mounted the lamp. This is the incandescent one, and then we had the lighting passport. I'll just bring the lighting passport. Just open the lighting passport. Yes. So here's the lighting passport, and I just sort of kept it like that. I kept it at a distance about maybe 10, 20 centimeters. But apparently, when I look at the measurements, I see that for the warm LED, for the cool LED, I brought it very close because I measured maybe 20,000 lux. For the other ones, for this one and also for the warm LED, I kept it at a longer distance. So I hope that answers your question. The second one, is a link to a video of the previous webinar available? We had the video of the previous webinar, but we only sent it to those who attended it. So I may repeat that at some other point. Normally, the webinar that I give is only to basically describe the basic science. But at some point, some people said, "Why don't you just do measurements, real-time measurements from the light, different lights?" So that's why I changed it in January 12. I measured from the real lights, and this time I only interpreted that. So in a few months, I'll give that webinar again. But if you really need it, you can send me an email. I can send it to you. I don't think it's a problem. So here's my email. I'll type it for you. rmanny@alliedscientificpro.com. Alliedscientificpro.com. Yeah. So you can email me, and if you need the link, I can send it to you. Any other questions? You can unmute or you can type. Are there any other questions? Anything you want me to go like from the measurements? So basically I described all these parameters that we measured. If you think of any other question later on, you did not understand, or maybe I explained too fast, please email me and let me know what your question is. Les, do you have any comments? Our sales rep in California, he's here. Les, he made some valuable comments last times about different things. So there was an issue with Flickr, and there was also an issue with this Spectrum Genius transmission. I was wondering what is the photopic transmission, which takes into account the eye response function. So Les made a correction, and I would just show that very briefly, very briefly, what we talked about. So if you use the Spectrum Genius transmission, you get an average transmission and you get the photopic transmission of any like filter you want to find the transmission of. So we were wondering what's the difference between the two. So the average transmission is simply the average from 380 to 780, whatever transmission it is. And we did, had a small disagreement about photopic transmission, and Les correctly said that that would take into account the eye response function. So this is how you can calculate. This is the transmission function, which is just the average transmission, and this is the eye response function. So thank you for that. Do you have any other comments, Les, for this webinar?
Oh, I think it was extremely well done, and I appreciate it. Thank you very much, Rez.
Thank you. Thank you so much for attending. Anyone else uh, has any comments, questions? Just take a picture of. All right. If you think of something, please let me know. And once again, I apologize about the confusion about the link. Uh, One of our media people have left recently, so other people are trying to do it, and hopefully this mistake will not happen. Thank you for your time, and have a great day. Stay safe. Thank you. Bye.
Thank you. Thank you very much.
Thanks.
Thank
Bye.
you.
Thanks. Bye.
Thank
Bye.
you. Thank you.